The point C is called the balance point, and the length is the balance length. Okay, so far, have you noted? Okay, so let's go back to this diagram. In this diagram, this is AB and this is AC. Now let's say the balance length is L. So the potential drop here in this wire, the potential drop is going to be VAC. The potential drop is VAC. There will be a current. There will be a current in this primary circuit. Let's say there is I. Will there be a current in the secondary circuit at balance? In the secondary circuit, there is no current because galvanometer reading is 0. Here I is equal 0. Okay. So VAC according to Ohm's law, VAC is equal I into RAC, the resistance of the wire between A and C, but this one could be written as rho L over A. Here I, rho and A is always constant along this wire. So VAC is equal I rho A over L. But at balance, here also it is at balance, okay? According to Ohm's law, at balance, condition, VAC is equal to E. Agree? Here these two potentials have to be same, right? Then only the current flow in this circuit becomes 0. The current flow in this circuit is 0. Okay, so VAC is equal to E. Then E is equal I rho A L. So this is equal to a constant K. E is proportional to the length. So by measuring the length, just by measuring the length, we can find out the EMF E. This is equation clear. Let's write this later. E proportional to L. For now, up to this, is it clear? E is equal to KL. Note it down. Noted. So we know that V is measured in volt, L is measured in length, centimeter. So this is volt per centimeter. So we call K is the potential gradient of the wire. Potential gradient of the wire. Second, now we know that K is equal I rho over A. Rho over A. Now if K is constant, only V is proportional to K. Okay, if K is constant, V is proportional to L. So let's look how to keep K as a constant. Rho and A, rho comma A belongs to the primary, belongs to the wire. Okay, belongs to the wire. Rho and A belongs to the wire and is constant. Rho is the resistivity of the wire and A is the cross-sectional area of the wire, which is constant. I has to be kept constant. I has to be kept constant. So, what is the problem with keeping I as a constant? When we keep this circuit connected, there will be a continuous current flow. When there is a continuous current flow, the resistance in the battery, the internal resistance build up and the charge in this battery reduces. Therefore, the current in this primary circuit will reduce. To avoid that, we have to use a battery that can provide current, constant current for a longer period of time. Okay, we have to use a battery that can provide current for a longer period of time. So, to keep I constant, to keep I constant, to keep I as a constant, lead acid accumulator is used. for primary cell. For primary cell, E naught. So lead acid accumulator. This cell has the ability to provide constant current for a longer period of time. Okay, then automatically K becomes a constant. So this area is an assumption. We know that area is not going to be in true uniform. So we assume that it is uniform. Okay, there might be some errors in that. The potentiometer wire should not be overpressed. We know the reason, right? Now, in this equation, E is equal KL, E is equal to KL. Let's say you know the length, the balance length as 30 centimeter. The balance length was 30 centimeter. Now, can you find E? Sarah and Sajay, you have noted up to the third note, right? Do I need to scroll up? Okay, so we know the balance length as 30 centimeter. Now, if I ask you, what is the value of E, can you find without knowing what is K? Is it possible? It is not possible, right? Obviously, it is not possible. So, if you want to use the potentiometer to find the EMF of a cell, what you have to do is you have to find what is the value of K. You have to find what is the value of K. So, finding K, we call it as calibrating the potentiometer. Is it clear? Why we call it as calibrating the potentiometer, finding K? You can just think like this. In a thermometer, uh, we take the readings from the thermometer as 50 degrees C, 60 degrees C, and so on. But initially, someone should have calibrated these values, right? Someone should have found that this length L corresponds to 50. This length L dash corresponds to 60. So someone found these lengths and they marked, and that is how they calibrated. Similarly, here, if we find out K, then only we can find the value of E. Therefore, finding K is known as calibrating the potentiometer. So next note, finding or determining the value of K, the value of potential gradient K, potential gradient K is known as calibration of potentiometer. Okay. So now let's think. To find K, you need to know the value of L and you need to know the value of E. Then you can find the value of K. If someone uses a battery E1, he will get a value K1. If someone uses another cell E2, he will get another value K2. So now there's a problem, right? Depending on the cell they use, the K changes. So because all the values will be closer, K1, K2, all of them will be almost similar, okay? Because depending on E, L will change according to K, but we have the same problem. Can you remember? The cell quickly discharging, or they don't have a uniform current, they don't have a constant current. We have certain problems like that, okay? The EMF doesn't remain the same for a long time. So we have to go with a standard cell. We have to use a standard cell. The standard cell we use to calibrate is called Western cadmium cell, okay? Using Western cadmium cell, which produces a stable EMF, a stable EMF of 1.018 volt is used to calibrate the potentiometer. So the setup will look like this. I'll draw it in the simplest form. This is E naught and now this is ES. This is where we are going to use the cadmium cell, okay? And this is the length L, the balance length L. So here ES is equal K times L. So K is equal ES over L. Okay. Now the potentiometer the potentiometer can be used to measure EMF and potential difference. Okay, now we can use to measure EMF and potential difference. So at balance, the current through this is 0. Noted. So next experiment, comparison of EMF of two cells. So this is our primary circuit. And this is our secondary circuit. Now secondary circuit, now we have to make a small change. This time we are going to have two cells. Because we are having two cells, we are going to use a two-way switch. At a time it can connect to cell E1, and at another time it can connect to cell E2. So this is E1 and this is E2. This one can connect between E1 and E2. The remaining setup is similar. We have a high resistance to protect the galvanometer, and then we have the sliding key. So here we have a variable resistor. This is E0 and this is E1 and E2. So here first we close this switch K. So let's say this is K1 and this is K2. When K1 is closed, when K1 is closed, we have E1 is equal K times L1. We will have a balance length L1, okay? When K2 is closed, we have balance length E2 is equal K times L2. This is the first equation and this is the second equation. So from 1 and 2, from 1 comma 2, E1 over E2 is equal L1 over L2. E1 is equal L1 over L2 times E2. So we have a y equal mx format graph. Y equal mx form graph. Okay, so note up this quickly. So if we plot the graph, we should get y equal mx for E1 and E2. So the gradient will give you m is equal to tan theta, that is equal E1 over E2. So straight away finding the gradient will give you the ratio between them. Sarah, done. Now, here there's a problem. The problem is to plot E1 versus E2, you must get, now just look, sorry, here a small mistake. It should be L1 is equal E1 over E2 into L2, okay? Make that change. It should be L1 is equal E1 over E2 into L2. We are plotting. You have to change the graph also. L1 with L2. Now we have a problem. The problem is, let's look, E1 is equal K times L1. Okay. Here, if we vary the length, only we will get another data point to plot. Or otherwise, always the balance length will be over here. Because this is constant, then this is also constant. So doesn't matter how many readings you take, always L1 will be here. So that is a problem. So how we can overcome that? We can change K. But let's look what is inside K. K is equal rho I over A. So we cannot change rho, we cannot change A, then we have to change I. How to change I? So what is I? I is the current in the primary circuit. How we can change the current I? Here we have a variable resistor. By increasing the resistance, we can decrease the current. Then K reduces. If K reduces, now E is equal KL. K reduce, L increase. So we will get a new balance length for L1 and L2. Is that idea clear? How we are going to vary L1 and L2 to get data points? Sarah, do you understand the concept? Okay. So let's write it down. To obtain by varying or by adjusting the value of the variable resistor, by adjusting the value of the variable resistor in the primary circuit, the set of readings, for L1 and L2 can be obtained. We know that E is equal to KL, but E is constant. Let's say E1 is equal to K times L1, then E1 is constant. To vary L, K has to be varied. K has to be varied. Okay. If I want to change L, I have to change K. But K is equal rho I over A. Rho and A are constants. And I is the current. Is the current in primary circuit. In primary circuit. By changing, by varying R, by varying R, I is varied. Hence, K and L and balance length L. If it is clear. Sarah. So, not when E1 is varied, sorry, when E1 is replaced with unknown EMF E and E2 and E2 is replaced with EMF ES. E over ES could be found, hence E could be determined. E could be determined. So in the previous case, I mean, in the previous experiment, we found K. After finding K, we found E, right? But in this experiment, using this comparing EMF, we can straight away find E without finding K. Is the difference clear between the previous and this experiment? Here we can just compare any two EMF. If one of the EMF is the standard, then we can calculate what is E. Without getting the ratio, we can straight away find what is E. Okay. Noted. Do you understand this? And now you might have a doubt. then why did we find K? What is the purpose of finding K, right? When we can do this experiment this way, why do we really need to find K? You will get that doubt. So the potentiometer, we can use this one to find EMF as well as potential difference. For EMF, we can go with this method, but for potential difference, if I want to find the potential difference across something, then we will have to know what is K. Okay. So let's look at an example. The meeting might end. You can try the example if the meeting ends. I will post the answer in the group if you need. Give a try. There are some phase two questions also related to this potentiometer concept. Before that, try the meter bridge concept. And if you have any doubts in them, you can ask. After that, let's discuss this potentiometer also. In potentiometer, we have one more experiment determining the internal resistance. Once we discuss that, we have completed the electricity part without the electromagnetic induction. Okay, so the remaining part is electromagnetic induction.